This is a lesson on sources of magnetic fields and a unit on magnetism. In a prior lesson on magnets, I had gone over what magnetic dipoles are and how all magnetism is created by electric charge in motion. So as we're looking at the sources of magnetic fields, we're going to be looking at charges in motion and specifically currents. And so we were talking in the prior lesson about how an electron moving around an atom is considered a current. It's a moving charge, and that creates this dipole. So when we look at the shape of the magnetic fields due to currents, we will keep this dipole figure in our heads and have it make sense with the shape of those magnetic fields. So magnetic fields, there's a couple of just main current distributions that we worry about. There's a long straight wire, which you see over on the right here, a loop, which you see down here, and then also a long set of loops, which is called a solenoid, which I'll get to in a little bit. And I wanted to highlight here on this slide the direction of the magnetic field at important points. So before we get into calculating anything, we're looking at just the direction. And so for a long straight wire, this is the most basic way to think about a wire, right? It's just long and straight. And the magnetic field goes around in a circle of that wire. And so how right-hand rule works for that is you put your thumb in the direction of the current, and then whichever way your fingers curl, that will be the direction of the magnetic field. And so for a long straight wire, this one's up. The magnetic field curls around it in this direction, and you can see those arrows. And the field is, of course, always tangent to the continuous curve at whatever point you're at. If I look at this wire directly from the side, so this is a side view, and remember we're getting used to looking at these things in 3D. If I have current going upward, if I'm on the right side of the wire, my fingers are into the page, and then on the left side of the wire, they're out of the page. So that's how to figure out the direction for just a long straight wire. For a wire loop, it is just as intuitive. What you're going to do is curl your fingers, and in this case, when you curl them, it's in the direction of the current, and your thumb is the direction of the magnetic field. And so for a loop like this, the only point we're really interested in the magnetic field is right in the center of this loop. And so you can see if you do right-hand rule and get the direction of the magnetic field at that point B for all of the points of the wire along this current, it will be pointing upward in the center here, directly upward. And this makes sense because of magnetic dipoles. If I think about the prior slide with an electron moving in a circle, that's the dipole that we saw. And so this is sort of the north side of this loop, and this is the south side of this loop. Over here, there is no north and south really. The magnetic field goes around in a circle, and it's a continuous loop. My biggest tip for trying to find direction of magnetic field due to current is trust your intuition on what thing is straight, and that will be your thumb, and what thing is curly, and that will be your fingers. And you can see in these two situations, it's opposite. One's a current, and then the curly is the magnetic field, as opposed to over here, the curly is the current, and the B field is your thumb. Now that I've established how to find the direction of a magnetic field due to a current, we can talk about calculating the magnetic field. And I had brought up this idea in a prior lesson, magnetic fields and magnetic flux. And looking at the field there, here we're actually talking about calculating the magnetic field, including the current. And what the big idea to drag along here is that there's a fundamental relationship between the gradient in space of that magnetic field, right? It curves through space, and there's some sort of gradient to that, and the geometry of the current distribution, whatever that is, whether it's a circle, whether it's a bunch of circles, whether it's a long straight wire. That magnetic field shape depends on the geometry and the magnitude of that current. And so we looked at flux, and that's one way to approach calculating magnetic fields, is to look at flux and magnetic flux through surfaces. And I grabbed these pictures from the University Physics text of OpenStax, Volume 2. And you can see that there's some complex things going on with calculus. There's a surface integral down here, there's a line integral, and those are not always the easiest thing to do, but the trick is to pick a nice symmetry. And without going into the details of how to use calculus to derive equations, I'm going to just present these equations to you. The concept that I need you to understand before we move there is this idea that the amount of flux through an area depends on the current and the area that you choose. And this is a dot product as well. So we really are looking at a specific angle between that area vector and the magnetic field. The other thing is, like I mentioned on the prior slide, there's a fundamental relationship between the gradient in space of that magnetic field, the shape of the magnetic field, and the shape of that wire. For instance, here we just have a part of a circle of wire. It's just a piece of wire. It doesn't extend in a whole circle. So the magnetic field of that is not going to be some simple equation. You would have to integrate over that distance. The takeaway is that the magnetic field depends on the amount of current and the distance away from that current. You can see that here. There's an R vector here. And you can see it in the equation too. There's an R here. So the current's in there. And so when we look at these equations, we're not surprised. And so I'm just going to cut to the chase here. Calculating magnetic fields due to these basic distributions. At an introductory level, we just look at nice basic ones that have applications in the real world. So the three fundamental symmetries is a long straight wire, and you can see that here, a current carrying wire and the magnetic field. If the field is circling around in that direction, that's what I'm saying. I curl my fingers in the direction of the magnetic field, and the current must be to the left. Okay. If I want to calculate that, for any distance r away from this magnetic field, it could be over here, another r2, whatever distance that is, it depends on I, mu naught, which is a constant, 4 pi times 10 to the negative 7 Tesla times meters over amps. There's a radius down in here as well. So that's for the long straight wire. That's the equation for the long straight wire. The loop, here's just a loop. If I take a long straight wire and wrap it into a loop, you can see the magnetic field here. And this is the distance r. In the wire, this little r is variable. But in the loop, that r is a value. Whatever the radius of this loop is, that is the r in there. And the currents in there as well. So you can see that equation. A long loop of wires, so if I take this here and I just line up a whole bunch of them, it turns into a really nice magnetic field that has a lot of applications, and so I'll talk about that in a little bit. But that's the equation there. It depends on the number of loops and how long that thing is. It's a solenoid, and the current through it. And so that's the simple equations. I picked out from the Hewitt Conceptual Physics text, I use the 10th edition here, the iron filings around a wire carrying a current. And these are the three different geometries. So that's what you're seeing here, these shiny silver things against this blue purplish background. Those are iron filings. And what we know is iron is ferromagnetic. It will align in a magnetic field. And you can see that it creates the shape of the magnetic field. If you do lab, this is a very standard introductory physics lab, is to just shake iron filings next to a wire or a magnet and see what the magnetic field looks like. And so you can see that here it's radial symmetry. For any r, it'll be a constant magnetic field along that r. And as you move outward, the magnetic field will get less. Here's for a loop. You can see the circling happen around each side of the wire here, and right in the center, that's what we'll be worrying about, right in the center here, it is perfectly aligned in one direction. When I take a bunch of those loops, that's why I'm saying, when I take a bunch of those loops and I line them right up next to each other, this is a solenoid, and you can see right in the center here, there's a magnetic field. And it turns out that magnetic field, because of all of the number of loops, the geometry, it's very constant in that region, and it points in one direction only. So it's a very useful magnetic field. So just to review a little bit and do some practice problems, I'm going to talk about each distribution separately again, just to go over details and apply the concept to a problem. So the first geometry I talked about was the long straight wire. Again, we're using right hand rule. Align your thumb in the direction of the current, and then your fingers will curl in that magnetic field. I put the value of mu naught down here, 4 pi times 10 to the negative 7th. So when you plug that in, the 2 pi's, there will be some canceling in the equation. And remember, this is for radius r away from the center of the wire. Anywhere along this wire, you can have this radius r, and it will be the same magnetic field along in this direction as well, for that radius r and for any r along that wire vertically. So I picked a problem. This is a classic problem we look at with this situation, is two parallel wires. It says two wires 3 meters in length are 48 centimeters apart from one another. They carry currents of 1.8 amps and 4.3 amps in opposite directions. I'm going to stop there and draw a picture so that I can have that going on. So let me draw that over here. I'm going to have, let's call this I left. And then obviously this one will be in the opposite direction. I'll call it I right. Okay. So we have the values and they're going in opposite directions, and I can make a note here that the distance between them is 48 centimeters, so 0.48 meters. Okay, so now that I have it drawn, I'm going to see what part A wants. Determine the net magnetic field at a point halfway between them. Okay, so I'm going to label some point P halfway between them, and I need to figure out the net magnetic field. Well, magnetic field is a vector, so I can add the magnetic field as vectors, and I'll have two vectors here, one from I left and one from I right. So I need to figure out, I'm going to draw those vectors. And what I'll do is I left first. So if I draw the magnetic field due to I left I have drawn going upward. When I extend my fingers to the right over to point P, I see my fingers are moving into the page. All right, so into the page. So I'm going to draw here, and this is, I'm going to call the magnetic field due to the left wire. I can make that a little bit bigger so you can see it better. Okay, so let's do it for the right-hand wire. Right-hand wire is pointing downward, and over at point P, when I extend my fingers, my palm to the left, I see that my fingers are curling into the page as well at that point. So when I look at point P, the magnetic field to the right current is going also into the page. Okay. I like to do this. We drew them in opposite directions. I think it makes a lot of sense to draw the currents in the plane of the page. But if I draw the currents from a side view, if I do a side view, if I look at it from this direction, this current is moving away from me, IL, and this current is coming at me, IR. Point P is in the middle here. And I'm doing this because you may be able to see the magnetic field a little bit better if I draw it here. So let me get this out of the way, and let's do this. For IL is going into the page. So I'm going to put my thumb into the page on the side view. And at point P, it's pointing down. So the magnetic field due to the left-hand wire in this view, it's pointing into the page, but when I look at it from the side view, it's pointing down. And the other vector is also pointing into the page, so I know in this situation it is also pointing down. So I'll call that BR. And that helps me a little bit. These are going to be the two vectors that I'm adding together. And you can see why it's important to draw those vectors, because just because the two wires are pointing opposite one another doesn't mean you just subtract their magnetic fields. You have to look specifically at the point. If we were in this region over here, they would be a different orientation. If we were in a region over here, they would be a different orientation. And so this picture down here I think is more reminiscent of when we did electric fields due to charges. You look at the charge and you look at the electric field due to each charge. Well, in this situation, we have currents, and you look at the magnetic field due to each current. So if I'm finding the net magnetic field, B net, that'll equal BL plus BR. And I'm going to put a vector equation on this. Just to remind you, these are vectors. I have to add them in vectors. If they were at angles with one another, I'd have to do x and y's, and I have another lesson associated with that technique. But in this situation, they're in one dimension. I'm just going to add them together in order to find this net magnetic field. So BL and BR, I'm ready for the equation here. Mu naught IL over 2 pi RL, and that'll add on to mu naught IR over 2 pi RR. Okay. The radius I'm going to look at here, the radius seems to be the same for both of them. It's half of the 0.48 meters is RL and RR. IL and ILR are different from one another, but those other things factor out. And so I'm just making this a little bit algebraically simple in order to solve the problem. So that's easier to solve than plugging all those values in for both terms. So I'm going to write in what I know. Mu naught is 4 pi times 10 to the negative 7th. I have that over 2 pi over 0.48 over 2. All right, and then I'm going to add the two currents. So I have 1.8 plus 4.3. All right, so when you run all of this through the calculator, the net magnetic field is 5.083 repeating times 10 to the negative 6 Tesla. And you can simplify that to be 5.1 microtesla. Okay, so right in the center there. If you wanted to find for a different point, you would have a different radius for the left, a different radius for the right. You would have to figure out the direction of the magnetic fields depending on what region it is. But for this situation, it was fairly simple and straightforward. So that was part A. Part B says, determine the force one wire exerts on the other. Are these forces attractive or repulsive? Okay, so I'm going to get rid of what I have in here. I don't need this stuff for now. We're not looking at point P anymore, so when I look at this diagram in here, I'm not looking at point P anymore. Point P can disappear, and I'm going to get rid of all of that stuff. I do still have my two currents, so get rid of that. Determine the force one wire exerts on the other. And so I picked this problem because this is typically something students struggle with, is that if there were no right-hand wire, let's imagine the right-hand wire isn't there, there would be a magnetic field at this point due to the left-hand wire. Even if the right-hand wire wasn't there, there'd be a magnetic field there due to the left-hand wire. So what happens is now we're putting this wire, the right-hand wire, in the magnetic field of the left-hand wire. So we'll put a current in here. So there's two steps in here that's going on, is that there is a B field due to one wire, and then the other wire feels a force due to that first magnetic field. Okay, so the magnetic field due to a wire, we know how to find that, and that's something that we can calculate easy. We have the value of the left-hand wire. We know the distance over to that spot is 0.48 meters, and we would be able to calculate that magnetic field. And so that's that equation. If we want to find the force a wire feels once it's in a magnetic field, the force on a current-carrying wire in a magnetic field is the Bill equation, okay? And so in this situation, the force is going to be on the right-hand wire from the left. And I haven't talked about direction yet. Let's think about direction. Now that we know that we're looking at a force on a wire in a magnetic field, let's look at those two vectors a little bit more particularly. Because I put BL over here, but that's not the direction. We need to figure out which direction it is. And on the previous part, remember the magnetic field in this region is going to be, IL is into the page. I'm pointing my thumb away from me. And then the region is over to the right, and I can see that it would curl downward. My fingers curl downward to the right of IL. And so the magnetic field due to the left-hand wire is going to point downward in this region. IR is pointing outward. So when I figure out this force, my thumb is out of the page because the current is out of the page. My fingers will point downward because the magnetic field is downward, and my palm points to the right. So what we're seeing is this force on this wire is repulsive, and I'm going to call this the force on the right wire from the left wire. What I'm going to point out is the same things going on for the other wire. The other wire has its own magnetic field, which is downward, right? So the B field due to the right wire is acting on the left wire, and the left wire is also feeling a repulsive force in this direction. So this will be the force on the left wire from the right wire. So this is a repulsive force, and I still need to find the magnitude of it. So this is why I'm doing this problem. It's a little bit more complicated strategy-wise. You have to find the magnetic field due to one wire and then put the second wire into it. So what we're going to do is write down the equation for the force. The force on the right from the left is going to be the magnetic field due to the left, the current in the right, the length of it, and then we'll deal with the sine theta. Sine theta actually in this situation is very easy. You can see that there's a 90-degree angle between the magnetic field and the current. The current is out of the page, the magnetic field is downward, and that's a sine 90 degrees. Okay, so that's how we calculate the force. Let's plug in a little bit more what we know. How to find the magnetic field for the left-hand wire. Like I said, we know how to find the magnetic field for a wire. Mu naught, this is the magnetic field due to the left-hand wire, so I'm putting the left-hand current in here. And so I'm going to do 2 pi over the radius, and in this situation, we're looking at a point, a distance d away from that left-hand wire. So d goes down in here. We still have IR, L, sine 90 is 1, and so I'm just going to leave it like that. So when I look at this equation, it depends on both currents and the distance between them. If I were to calculate the other one, I would have IL here and IR here, and I'd end up with the same equation, and that's what we expect from Newton's third law, is that these two forces are equal and opposite to one another. So now I have the equation. I can write this out. Mu naught is 4 pi times 10 to the negative 7th, IL 1.8, IR 4.3. The length, they tell me, is 3 meters, and I'm going to divide that by 2 pi times the distance between those two wires, which is 0.48. The pi's cancel. I have a 2 here. You can run this through your calculator, and the force on the right-hand wire from the left-hand wire is 9.675 times 10 to the negative 6 newtons. So kind of small force, but they are a large distance apart. For currents and this magnetic field, this is a large distance apart, so it's not a large magnetic field. So now that you know how to calculate magnetic fields and find their directions, you're going to do the regular things with them that you would with other vectors, such as find a net magnetic field. And then also, now you know how to find magnetic fields from wires to put other wires or charges in. So these are nice equations to know. The next geometry was just a plain circular loop. What we're going to do is look at the magnetic field directly in the center of this loop. And so this is the radius r here, and that is the r in this equation at the center of the loop. This equation does not count for any other point other than directly center in that loop. You can see with the geometry that the magnetic field will get less as you move out here. Remember, density of field lines gives the magnitude, the relative magnitude of a field. And so they're farther apart out here, and the magnetic field is less. But we can see that they're really tight together here, and they're pointing directly upward. And so we can use that fact and this equation to have something happen with the magnetic field right in the center. I wrote a pretty simple example here. A circular wire 15 centimeters in diameter and having a current of 1.8 amps is placed immediately adjacent to another circular wire 10 centimeters in diameter and having a current 4.3 amps in the opposite direction of the first. Okay, so I'm going to draw a picture here really quick so that we can get a picture of the situation. So there's a 15 centimeter diameter loop. I'll have the current go, let's say, downward here. And I'll do right-hand rule. If I do current downward at the front of the loop, that means my fingers are pointing downward, coming at me. They come out of the page at the top and go downward, coming. And that causes my thumb to be towards the right in this situation. So I'm going to call this B1 for going with I1, which is the 15 centimeters at 1.8 amps. There's another circular wire immediately adjacent to it. So let me put another circular wire in here right next to it. And this is the 10 centimeter one. And so they're right next to each other. The current is moving in the opposite direction, so I'm going to put the current going upward on the front side of that loop. Okay, so it would be going upward, coming out of the bottom and going into the top and going upward in the front. And I can see my thumb is pointing to the left in that situation. I'm also going to note that the radius is smaller and the current is bigger, so the magnetic field due to I2 is going to be larger than I1. So there's B2. I'm going to do the same thing I did on the previous problem. B net has to equal B1 plus B2. And so in this situation, and maybe we can assign a coordinate system, we can say this is the positive x direction. It's arbitrary. So we're going to get B1 minus B2, and I expect this to be a negative number because B2 is larger than B1. So that's how we would find B net. So I'm going to plug in what I know about these magnetic fields. B1 is going to be mu naught I1 over 2 R1, right? That's the equation there. And then minus mu naught I2 over 2 R2. There's some common variables in here. The mu naught can come out. And then also I'm given the diameters, so I'm not going to factor that the 2 out. I'm going to leave these together. This would be diameter 1 and this would be diameter 2. So I can factor the mu naught out. I get mu naught I1 over diameter 1 minus I2 over diameter 2 quantity. And so let's multiply this out. I get 4 pi times 10 to the negative 7th. That's mu naught. I1 is 1.8 and its diameter is 15 centimeters, so I go 0.15. I subtract this, I get 4.3 over 0.1. And it turns out when you do this in parentheses, it's negative 31. I didn't do that on purpose. It's just this nice round number. And it's negative, just as we expected. B2 is going to be larger than B1. So we get this negative number in here. Multiply this by 4 pi times 10 to the negative 7th. And the net magnetic field is 3.89557 times 10 to the negative 5th Tesla. And if you're clever, we're just going to put in here 39 microtesla. And so that is that net magnetic field. Note that I was really keeping track of the direction of these vectors and the relative magnitude and what I expected. It doesn't say, it says magnitude and direction, so I'll say left in my diagram, or negative x. If I assign a coordinate system, I could say it's in the negative x direction. The last distribution we have to look at is the solenoid, which is a long loop of wires. You can see a long loop of wires here. And I like this diagram over here because it really shows the net effect of each wire. I had shown you the picture earlier that had a bunch of magnetic fields due to each wire, but this shows them all added up. And you can see right in the center, right in that center there, this is where we would want to do some sort of experiment. And across this whole cross section, it's going to be constant in there. And so that's why we like solenoids, is at the ends, it's not so reliable. You have not a constant magnetic field at the ends. But right in the center, all the way across the center, you have a constant magnetic field. In a lab, I would have people connect a slinky up to a voltage supply. And then you can use a Hall probe in order to measure the magnetic field in the center. It's a really cool experiment. And so the direction of the magnetic field in here, the dipole sort of effects of the magnetic field, depend on the current. And we can see that in this situation, we can put the I wouldn't do it that way. I do it this way. I curl my fingers in the direction that the current's moving, and then I get my thumb to the left. And you can see that's what's going on here. The direction of the thumb is the direction of the North Pole. So this vector over here need to be reoriented. Highlight here, one of the things that I see students have trouble with using this equation is really understanding what little n is. Little n is the number of loops per unit length. Loops per meter. Okay, so when I look at this, there's some sort of unit, there's some sort of length, L, and there's some sort of n, right? I count them up. Each loop I count, and I would get an n number of loops, and that's what little n is the number of loops divided by the length in meters. I picked out an interesting problem. I borrowed this from Cutnell and Johnson in their back of the chapter problems. A solenoid is formed by winding 25 meters of insulated silver wire around a hollow cylinder, and that's a pretty easy way of just creating a solenoid. The turns are wound as closely as possible without overlapping, and the insulating coat on the wire is negligibly thin. Okay, so I'm getting a picture here. I'm going to take a long straight wire, right? Okay, so we have a length of wire, 25 meters. And we're going to take that wire and we're going to wrap it around a hollow cylinder. So whatever this 25 meters is, it gets wrapped in a circle a bunch of times. And we're going to have n number of loops. And then this is the length L of the solenoid that we're looking for. So I'm going to erase this L here and just call this maybe little l. The big L that we refer to for solenoids is the length of the solenoid, not the length of the wire. So that's why I like this problem. It really makes you distinguish what's going on with the length of the wire and the length of the solenoid. Let's see what they want us to find. When the solenoid is connected to an ideal battery, so there's no internal resistance, we're actually getting a terminal voltage of 3 volts. The magnitude of the magnetic field inside the solenoid is found to be 6.5 millitesla. Determine the radius of the wire. So we don't want the radius of the solenoid. That's not what it's asking for. They want the radius of this wire. So whatever this radius is, r. Which is kind of interesting that we can relate the radius of the wire to the magnetic field. And what I think about, now go back to this picture here. This is a nice picture because you can see in here this wire has a radius, right? So the thickness of one wire is going to be 2r. And we're going to take that wire and wrap it. So there's a 2r and then another 2r and another 2r. And all of those 2r's are going to add up to the length of the solenoid. So this relationship isn't really too bad. When I look at the length of that solenoid, I'm going to have n number of loops times 2r of their length, right? When I add it all up, one wire, one wire, one wire, they're all next to each other. I have n number of wires, and they're all a thickness of 2r, and when I add them all up, that gives the length of the solenoid. So it feels like I got the hard part of this problem out of the way, is determine the radius of the wire. So wherever I see L, I can put in this relationship that the length of the solenoid is related to the radius of the wire. So let's look at the magnetic field due to a solenoid. Let's write this in. B solenoid, the magnetic field equals mu naught N, which is big N over L, times I. Oh, there's an I term in here, and I'm not given the current. I'm only given a voltage. They do tell me that this is a silver wire, and so I'm thinking in terms to find the current, I can take a voltage and divide by a resistance, right? Ohm's law says that I can do that. If I have a voltage, which is 3, I can find the resistance. Well, the resistance, I know how to find the resistance of a wire. I have the physical resistor is going to be rho, the resistivity of the wire, and I have silver, the material silver, area divided by length. And the area in here is the area of the wire, which I can calculate. The area of this wire is going to be pi r squared, this radius of the wire that I'm looking for. The length of the wire is the 25, so maybe I shouldn't put big L down here. I should put the little l down here. This wire that's offering resistance is 25 meters long. Okay, so there's more terms that we can put in this equation. B equals mu naught N over L, and I know L is N times 2R, so I can put that in there. And then I, now I have an expression for I. I is going to be V over R, which is V over rho A over L. So that becomes VL over rho A. Okay. A I can plug in as well. So I get VL over rho pi R squared. Very good. So let me plug that in up here. VL over pi rho R squared. Okay, so we're getting an R dependence here, R cubed. N cancels on top and bottom here, and I'm solving for the radius. So let me solve for this, R cubed. I'm going to have to move R cubed over this side, so everything on top here stays. Mu naught VL, and then on the bottom, I'm still going to have a 2, a rho, a pi, and that B field needs to come over. So R cubed goes up here, B comes over here, and I just simplified that term. Okay, so mu naught I know is 4 pi times 10 to the negative 7th. V, they tell me, is 3. The length of the wire is 25. I'm going to divide by 2 times the resistivity of silver. The resistivity of silver we can look up in a chart someplace. I get 1.59 times 10 to the negative 8th ohm meters. That was from the OpenStax text. And then I have pi still, and then the magnetic field 6.5 times 10 to the negative 3rd Tesla. A pi cancels here and here. And when I run this through the calculator, I get R cubed is